Okay, good afternoon. So today we are in section 7.5. We are doing applications on Laplace transform to solve initial value problems. Initial value problems are just differential equation plus initial conditions. Now let me tell you the steps that you need to solve or to apply Laplace transform to solve initial value problem. You need first to take the Laplace transform of both sides of the differential equation. Number two, plug in the initial conditions. So plug in the initial conditions. Number three, solve for the Laplace transform. So you solve for big Y of S, yeah. And number four, take the Laplace inverse of both sides, yeah, to get Y of t, yeah, Y of t. And you may need to, so when you look for this, remember that when you go with Laplace inverse of y big of S, then you need to go for table 7.1. Yeah? Now, let me give you an example. So let me apply this and tell you how to apply Laplace transform to solve a question from the textbook. So here is question number 1. It says, solve the given initial value problem. Solve the given initial value problem using the Laplace transform. Okay, what is the differential equation or the initial value problem? It says you have y double prime. Let me write it big here. Y double prime. Let me write y double prime minus 2y prime plus 5y equal 0. Where we need the initial conditions, y of 0 and y prime of 0. So what is y of 0? Y of 0 is just 2, and this is 4. Yeah. Now let me go and apply the steps. Here is the solution. So we have that differential equation. So minus 2y prime plus 5y, and let me here write equal to 0. Now the first step is to take the Laplace transform of both sides. So here is the Laplace transform of both sides, yeah. And then Laplace is a linear function, so you can distribute the Laplace, and then you're going to have here, let me write here, so we're going to have Laplace of y double prime, and now also I use linearity here and I take the minus 2 outside the Laplace transform, then I'm going to have minus 2 Laplace of y prime, and then plus 5 Laplace of y equal Laplace of 0. Yeah? Now keep in mind that Laplace of 0 is 0 because it is the integral of 0 from 0 to infinity. Then this will be 0, right? Because it is an integral from 0 to infinity. If you plug in that integral f of t equals 0, then you will get 0. Now let me go and use the second derivative rule. If you go here to the table here, if you have the second derivative, then the Laplace transform is s squared y capital of S, which is the Laplace transform of y small, minus s y small at 0 minus, it is the same minus here, minus y prime at 0, the derivative of y of t at 0. Now this means if you go with this guy, the first guy here, then you're going to have s squared and you're going to have y capital of S. Remember that this is a function of time, and now you are changing it to a function of frequency. And then here minus s times y at 0, small y at 0, and then minus y prime at 0. It is also small y at 0, right? All that thing is just Laplace transform of y double prime. Now minus 2, and then we have Laplace transform, so I'm going to write it as a bracket here. Now again, I'm applying now the Laplace transform from the table. I'm adding it to the table. Laplace transform of the first derivative is just s times the Laplace transform of the function, which is big Y of S, minus the value of the function, the small y at 0. Now I'm going to have s y capital of S, and then minus y small at 0. Yeah? And then we have that 5y now. I'm writing it here, plus 5. Laplace of y is just big Y of S. So this guy here is just, let me just show you. So I'm going to tell you that this guy here is that guy. And this guy here, Y double prime, so here, double line is this double line. And that guy here is that guy, okay? Now let's continue with this and show you how we're going to solve this initial value problem. So we don't need the title anymore now. So you need now to simplify and solve for y capital of S. So you solve the equation for y capital of S, then you're going to have the Laplace transform of your solution, and you go back and search for the Laplace inverse. Now let me show you what we got now. We got the following. I'm going to write it here again. So we have s squared y big of S, right? And then here minus s y of 0, yeah, minus y prime at 0, and then here plus, let me just write this, or minus 2, and then we have s y big of S, and then y of 0, yeah, and then we have 5 y big of S, yeah, equal 0. Now remember one thing, that we have the initial condition here, that y of 0 equal and y prime of 0 equal, right? These are the initial conditions. They are 2 and 4. Yeah, they are 2 and 4. Yeah. Now the next step, the first step is to take the Laplace transform of both sides. The next step will be taking the initial condition and plug them in the equation. So this is y of 0, so this goes here and also goes here. And then y prime of 0 is here. So let me go with y prime of 0, so it goes here, and that's it, right? Now finally we will have the following. So we will have s squared, yeah, and then we have also minus 2sy big. So let me write it step by step. Y of s. Now y of 0 is 2, then you get minus s times 2, so minus 2s, and y prime of 0 is 4, so minus 4, and then minus 2, and then we have here s, big Y of s, right, minus 2, good, and plus 5 y capital of S equal 0. Now the next step is to solve. Now solving, now simplifying, and solving for y capital of S. Okay. Now simplifying, first I need to multiply the bracket, yeah? So I need to multiply the bracket here. Then I'm going to have here minus 2sy capital of S, and I have already s squared, and I have a 5ys. Now you need to collect these things together, right? Collect these things together. So I'm writing here, I have y big of S, and I have here a coefficient for that. So you have s squared from here, you have minus 2s from there, and you have here 5. Yeah? So this is the coefficient of y big of s, right? Now what is left here is, now we have here minus 2s, and we have here minus 4, and here minus 2 times minus 2, you get 4. So you get something like minus 4 plus 4. This minus 4 is that, and minus 2 times minus 2, you get plus 2, plus 4, and it is here. Equal that 0, right? Now, let me continue with this. This cancel with that, right? And then I will add 2s to both sides of the equation. Yeah? And finally, I'm getting y of s multiplied by s squared minus 2s plus 5 equal to 2s, right? Now, what is the next step? So this is big Y of S, yeah? Now, the next step is we need Y big of S. We are solving for Y big of S. Now, for this reason, I will divide both sides over the coefficient of y big of s. So I will divide over s squared minus 2s plus 5. Then I finally have the following. I have y big of s equal to 2s divided by s squared minus 2s plus 5. So what we got here, are we done or not? Look at this. So what we are looking for, y of t, not the Laplace transform for y of t. So we have small y of t, which is the solution for the differential equation, solution for even the initial value problem. But we didn't get y small of t, we got y capital of S, which is the Laplace transform of that thing. So what is the connection between this and that? So this is the Laplace, if you like, this is the Laplace of y small of t. So this is the Laplace of your solution, but you need the solution. What is the good thing to do to get y small of t? So if you want y small of t, then you need to go back from a frequency function to a time function, a small y of t, a small y of time, function of time. So you need to do Laplace inverse of 2s over s square minus 2s plus 5. Very good. So what is next? Let me go now and check if I can find the Laplace inverse for such function. Now let me go with the degree for the numerator. So degree here is 1 and degree here, degree is 2. But I said if it is degree 1, degree 2, then you cannot do the long division. You need a partial fraction. But there is a special case says that if this is with power 2, then you can use completing the square. So you need completing the square. What is completing the square technique? Then you need to add and subtract b over 2a squared, right? This thing is just, this is a is 1 and b is minus 2. Then you add and subtract, just minus 2 or 2 doesn't matter because you are squaring here. Then you have 2 over 2 and then you get plus minus 1. This means that you need to add and subtract 1. This means the following. So you have 2s over s squared minus 2s, and then here I'm adding, so I'm adding 1 and then subtracting 1. It is like doing nothing, and here is the 5, right? And then this thing is just 2s over that thing here is just s minus, so let me write it like this. It is s minus 1 squared, and this guy here is 4, right? So, but the 4, I can write the 4 as 2 squared, right? So I'm going to have 2 squared. Yeah? Okay. So I'm almost done. Now I need to do the Laplace inverse. So my y of t now is just the Laplace inverse of 2s over s minus 1 squared plus 2 squared. Yeah? Now this 2, I can take it outside the Laplace inverse. So I can take the 2 here. Now let me go and compare with the table. So you have s up, s down with s shifted squared, and you have a number here squared. If you go and compare with the table, you're gonna notice that the closest one is this line, EAT cosine BT, right? For this reason, the only missing part is A here. So I'm missing A. So let me just first go and say, if you comparing with this thing, it is line 8, yeah? Comparing, yeah? If you compare with line 8, then you're going to have A equal to 1 and B equal to. But for the numerator, I have a trouble here because I don't have S minus A here. So missing A. So what is A? A is 1, but I can subtract 1 here and add 1, right? Now let me show you what's happening now. So here is the y of t is just 2 now, and then Laplace inverse. And then I need to cut this into 2 parts. This is the first part, which is, so let me just use the green. So I can cut this into 2 parts. The part that I was looking for, which is good. And then a second part here. A second part, I need to change the color maybe. Here is the second part, right? So we have 2 parts now, which are s minus 1 over s minus 1 squared plus 2 squared, right? And then here I have minus 1 over s minus 1 squared, and then plus 2 squared, right? Now this one you can compare now with the cosine. So this you go with, compare with EAT cosine BT. But this one here you have an S up, but here you have a number up. Then if you have a number and a number, then you need to compare with EAT sine BT, right? Now finally, what is the answer? Will be 2 and then times. We have A now, it is 1t, so t. And we have B, it is 2 cosine 2t. And then plus E t sine 2t, yeah? And we are done. So this is y of t, which is the solution for, which is, so done. So this is the solution for our initial value problem. I need you to be aware of something. Note that, here's a notice, note that we used the initial conditions in the next step. In the second step, in the second step. For this reason, final answer has no constants of integration. So by this remark, I can call this a remark here, yeah? By this remark, it says that in Laplace transform, you apply the initial condition in the second step, while in solving using indeterminate coefficient or any other method, first you solve and you get the general solution with C1 and C2, and then you keep the initial condition as a last step. So in other techniques, you leave the initial conditions to the last step, while in Laplace transform, you use the initial conditions in the second step. So let's solve another problem from the book. So I will solve now. I will solve question number 3. So here is another question here. So let me change the question. So it is asking the same thing. Question number 3. I will give you an initial value problem and I will ask you for the solution using the Laplace transform. So here is y double prime, yeah, y double prime plus 6 y prime plus 9y equal 0, with here y of 0 equal and y prime of 0 equal. Let me see what is, it is minus 1 and 6. So minus 1 and we have y prime of 0 is 6. Okay, very good. Now, I want you just to notice one thing. When you do the Laplace transform of both sides, then the coefficient for y big will be s squared plus 6s plus 9. So it is kind of, when you change for characteristic polynomial for the equation, or when you plug e power r, if you remember, you get r squared plus 6r plus 9. It is the same way here. You will get s squared plus 6s plus 9. So let me show you this. Now here is the solution. Step number 1 is taking the Laplace transform of both sides. So I have the equation, which is y double prime plus 6y prime plus 9y equals 0. And the first step is taking the Laplace transform of the whole equation or to both sides of the equation, then you will have the following. You will have Laplace transform of y double prime. So let me write here, Laplace transform of y double prime plus 6 Laplace transform of y prime plus 9 Laplace transform of y equal Laplace transform of 0. And we said Laplace transform of 0 is 0. Now there is a rule for this. It is the last row here. It is s squared. So just I want you to notice this thing, that this y, small y, is a function. It is y of t, right? While when I write big Y, then it is y of s. So I'm writing here y capital of s. And then the second thing is minus s y of 0. And then minus y prime of 0. That is that thing, right? And then here minus 6. And then I need here to be careful because plus 6. I need to multiply that 6 with the Laplace transform of the first derivative. It is here, Laplace transform of the first derivative is s y capital of s minus y of 0, yeah? And then the last thing is to add 9, and then the Laplace transform of y small is y capital of s, and this is equal 0. Now you need first to plug in the initial condition. So you take the initial condition here, you plug it here, and you plug it there. And then you take the initial condition, which is 6 here, and you plug it there, right? Now what you will get here, you will get the following. You will get s squared y big of s minus, so minus s times minus 1, you get plus s, yeah? And minus y prime of 0, you get minus 6. And then here, plus 6 times, so let me do it, 6 times this, and 6 times that. I don't know what is that, now I know it is minus 1, minus 1, you get here plus 1, times 6, you get plus 6. So why here minus 6? It is here, it is minus 6 here, yes. So this is the first part here. So I'm doing this. So this is the first part, right? And now I'm doing the second part. So it is plus 6. Let me write it in details. S big Y of S, and then here minus 1, you get plus 1. Yeah? And the last thing is just 9 y big of s equal 0. Yeah? Now let me collect, okay, let me multiply and then collect, yeah? So we're going to have minus 6 with 6 times 1, then I'm going to have that thing cancelled with that, right? And finally you will have s squared, so let me write like this. So y big of s, and you have a fraction for, not a fraction, coefficient for this. You're going to have s squared, yeah? And you're going to have 6s, and you're going to have 9, yeah? And then finally here, I'm getting s, yeah? Yeah? And then equal to 0. Very good. So what is the next step? What is the next step? The next step, let me just check this. Yeah, so we have s. The next step is to solve for y big of s. So the next step is to solve for y big of s. Then if you like, solve for y big of x, solving now, step number 3, solving for y big of s. Why you solve for this? So that you will be in the second column of the table. and then you go back and find your solution, which is a function of time. So you look for a solution which is a function of time. First, you find the solution as a function of s. So you find the Laplace transform of your solution. Now, what is that? Y big of s, if you like, it is just minus s. So it is just subtracting an s from both sides, and then dividing by that thing, which is s squared plus 6s plus 9. I want you to notice that the coefficient of y big of s looks like the equation, which is y double prime plus 6y prime plus 9y. Okay, it is not almost. It is like. It looks like the differential equation, which is the homogeneous differential equation, or the left-hand side of the differential equation. So here's what we have now. We have over s squared plus 6s plus 9. Now the next step, so you have the Laplace transform of your solution, and your job now is to get the small y of t. Now, what is y of t? This thing. Now you are in the second column of the table, and you need to apply Laplace inverse to get that thing. Now, if you want y small of t, or before doing this, I need first